Just take a look around you. I mean, right now. Look at the screen you're watching this on. Think about the air you're breathing, maybe the cup of coffee on your desk. Have you ever really stopped to wonder what all that stuff is actually made of, way, way down deep? Well, that's what we're going to do. We're about to uncover the hidden rules that run pretty much everything.
You know, this is one of the oldest questions humanity has ever asked. For thousands of years, we've wondered, is the world just one big, solid, unbroken thing? Or is it made up of countless tiny little pieces, totally invisible to us? The answer to that question, it turns out, changes absolutely everything about how we see reality.
Way back when, brilliant thinkers imagined that everything was a mix of 5 basic elements. Air, earth, fire, water, and sky. But modern science came along and told a different story. It started looking at matter's properties. For our journey today, we're going to zero in on the physical side of things, basically how all this stuff actually behaves.
So here's our game plan. We'll start by uncovering matter's biggest secrets. Then we'll dive into how its tiniest parts act, and how that creates solids, liquids, and gases. We'll explore how they change from one to another, and finally, we'll see this amazing science working in our everyday lives.
All right, so what is this tiny secret of matter? It's one single idea that completely rocked the world of science. Matter isn't solid. It's actually made of countless, individual, tiny things called particles. Now that is a huge claim. I mean, how in the world do you prove something you can't even see?
Well, check out this super simple experiment. You take a glass of water, right? And you mark the level. You toss in a spoonful of salt, and just like you'd expect, the water level goes up a little bit. But here's where the magic happens. You start stirring, the salt seems to just vanish, and the water level drops right back down to where it started. So, where did the salt go?
And here is the aha moment. The salt didn't disappear at all. Its tiny little particles just slipped into the empty spaces that were already there, right in between the particles of water. This simple kitchen trick proves 2 enormous things. 1, that matter is made of particles, and 2, that there are gaps between them.
Okay, so matter is made of tiny particles. That's one mystery solved. But that just leads to another question. Just how small are we talking here?
This next experiment gives us a clue, and honestly, it's mind-bending. You can take just a couple of tiny crystals of this potassium permanganate stuff and turn a whole beaker of water dark purple. Then, get this. You take just a little bit of that purple water and add it to another beaker of clear water, and the whole thing turns purple again. You can keep doing this over and over and over, and the color, while it gets fainter, is still there. Just think about what that means. Those first few little crystals must have been made of millions, maybe billions of particles, each one spreading out. They are unimaginably small.
All right, we've proven these tiny particles exist, and there's space between them. But what are they actually doing? Well, it turns out they're all playing by the same 3 fundamental rules, and these rules define the entire physical world around us.
So here they are, the 3 big rules. Number 1, as we saw with the salt, there's space between them. Number 2, and this is a big one, they are always moving. They're jittering, vibrating, and bouncing around all the time. They have kinetic energy. And number 3, they attract each other, kind of like tiny little magnets. The whole universe is basically a constant tug of war between their need to move and their pull towards each other.
And believe it or not, those 3 simple rules are the entire blueprint for the world we know. They're the reason we have solids, liquids, and gases. Every single difference between a solid rock, a flowing river, and the air you breathe just comes down to how their particles are playing by those rules.
This chart really tells the whole story. Let's look at a solid. The attraction between particles is super strong, so they're locked into a rigid structure. They can't go anywhere, they can only vibrate in place. That's why a solid holds its shape. Now in a liquid, that attraction is a bit weaker. The particles can break free and slide past one another. That's why water flows. And in a gas, the attraction is almost non-existent. The particles have so much energy they just fly around like crazy, filling whatever container you put them in.
So, if the state of something is just this balance between particle energy and their attraction, what happens if we mess with that balance? Well, that's when things get really interesting. That's when we see the great transformation, matter changing its state. And we have 2 main control knobs to do it, temperature and pressure. It's pretty simple, really. When we turn up the heat, we're just giving the particles more energy, making them move faster and faster. And when we apply pressure, we're squeezing them closer together, which makes their natural attraction to each other much stronger.
So let's start with a block of ice. As you add heat, you're making those locked-in water particles vibrate like crazy.
They rattle around faster and faster until finally, bam! They break free from that rigid structure. They start sliding past each other. The solid has become a liquid. We call that melting or fusion.
Okay, now let's keep adding heat to that water. The particles get even more energetic. They start moving so fast and so violently that they completely overcome the force of attraction holding them together. They escape entirely and fly off as a gas. We all know that one. That's boiling.
And this whole thing works in reverse too. If you take that hot steam and cool it down, you're literally robbing those particles of their energy. They slow down, and their natural attraction takes over again, pulling them back together into little droplets of liquid. That's condensation. You see it every time you have a cold drink on a warm day.
Then we have the weird one, the exception to the rule, sublimation. For a few special materials, like dry ice, the particles in a solid can get so much energy so quickly that they just skip the liquid phase altogether. They leap directly from being a solid straight into being a gas.
Now, this might all seem like something that only happens in a science lab, but the truth is, these principles are working all around us every single day in ways you might not even realize. Let's take a look at one of the most common examples.
We've all seen a puddle on the sidewalk dry up, even on a cool day. Obviously, the puddle wasn't boiling. So what's going on? That is evaporation. See, unlike boiling, which happens all through the liquid, evaporation is just a surface game. Only the particles right at the very top, if they happen to get just enough energy from the sun or the air, can break free and escape.
And what's funny is that we are all masters of evaporation. Why do we spread wet clothes out on a line to dry? We're increasing the surface area, giving more particles a chance to escape. We all know things dry faster when it's warm or windy. All we're doing is making it easier for those surface particles to make a run for it.
But here is the absolute coolest part about this, and I mean that literally. To make that jump from liquid to gas, an escaping particle needs an extra burst of energy. And it steals that energy from whatever it's touching, including you. That's why you feel cold when you get out of a swimming pool. The water on your skin is stealing your body heat to evaporate. It's why sweating cools us down. Evaporation is basically nature's air conditioner.
So solid, liquid, and gas are the big three we see here on Earth. But what happens if we push temperature and energy to the absolute extremes? Well, if you crank the heat way, way up, you get plasma, a super-energized gas. It's the stuff that stars are made of. And if you go the other way and cool things down to almost absolute zero, you get a bizarre state called a Bose-Einstein condensate, where the normal rules of physics just start to get weird.
So when you think about it, everything we see, a block of ice, a cloud of steam, even the sun itself, it's all just the same tiny particles performing a different kind of dance, all based on the same simple rules. We know that temperature and pressure here on Earth can create these different forms. So it just makes you wonder, right? Out there in the vastness of the universe, under the insane gravity of a black hole, or in the freezing void of deep space, what other, even stranger states of matter are just waiting for us to discover?